Okay, so in the last video, we looked at 45, 45, 90 triangles, and we looked at the sine, the cosine, and tangent of those. We have another special right triangle that we need to look at, and that's the 30, 60, 90 triangle. So we're going to focus on those first, then I'll recap it all, and then we'll take a look at a couple of examples, and then we should be nearing the end of this trig unit. We've got at least one or two more videos to go beyond that. So let's draw up a 30, 60, 90 triangle. Recall, that's just the measure of the angles. You've got the 90-degree angle there. Here's our 30-degree angle, and here's our 60-degree angle. If you recall from previous videos, and if not, go back and watch them. There's nothing wrong with watching them again. We talked about 30, 60, 90 triangles, and their measurements are always set up in a certain way, just like the 45, 45, 90 were. We start with the shortest leg. You have the hypotenuse, which is across from the 90. The shortest leg is the leg that's opposite the 30-degree angle, and what we did is we called that x. If that side is x, whatever it is, 5, 8, 117, the hypotenuse is always twice as big as that side. If you're not sure why that is, again, go back and watch the video. The other leg, the leg opposite the 60-degree angle, will be whatever the short leg is times the square root of 3. These things we need to have memorized. Okay? If you know those ratios, now we can take a look at some special trigs that we're going to memorize. In the last video, we looked at 45-degree angles, and we saw what the sine, the cosine, and the tangent were of those. We will recap those before we're done here. But let's take a look at the 30 and the 60-degree by themselves. So first, we're going to focus on the 30-degree angle. And so we're going to take a look at the sine of our 30-degree angle. Remember, sine, you always have to have an angle measurement after it, or something that represents an angle, either a letter or the actual angle measurement. I didn't put any letters for the angles, so we're going to go with the actual measurement. The sine of 30 degrees, recall that sine SOHCAHTOA is going to be the opposite side divided by the hypotenuse. Well, the opposite side is x, so we're going to put an x up here. The hypotenuse is 2x, and so we put a 2x down here. Now, if we put on the big girl pants and reduce that, they're both, x's can be reduced, but be careful, don't call that a 2. It's not a 2. The 2's in the denominator, and so this is actually 1/2. What this says is every 30-degree angle in the world, if you have a 30-degree angle on a flat surface, the opposites, and draw a triangle out of it, the opposite side compared to the hypotenuse will always be in a ratio of 1 to 2 every single time. That's powerful. If we look at the cosine of a 30-degree angle, no problem. Cosine, SOHCAHTOA, is the adjacent side divided by the hypotenuse. So if we look at the 30-degree angle, the adjacent side is x times the square root of 3, and the hypotenuse is 2 times x. And so again, reducing that, the x's cross out, and if we look at what we have left, we have a square root of 3 in the numerator, and we have a 2 in the denominator. That's a number. The square root of 3 is around 1.7. If we take 1.7 and divide it by 2, you get about 0.7 something, 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 something. Okay? That is always, always, always going to be the ratio. It always works out that way because of the way the 30-degree angle works. If we look at tangent, the tangent of a 30-degree angle for SOHCAHTOA, tangent is the opposite side divided by the adjacent side. So if we look at the opposite side, that's x, and the adjacent side is x times the square root of 3. Again, reducing that, those x's cross out, and so we end up with 1 over the square root of 3. And we're going to rationalize that just like we did in the last video with the 45s. I'm going to rationalize that because we don't want a radical in the denominator. So I'm going to multiply both the numerator and the denominator by the square root of 3. That's something we did back in August. You may have forgotten about that. That's okay. As long as you understand the concept here, no big deal. So our numerator becomes 1 times the square root of 3, which is the square root of 3. Our denominator, the square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is just a 3, no square root sign. Okay, so that is the tangent of every single 30-degree angle in the world. If we look at the 60 degrees, we're going to see some very similar things. If we go to the sine, if we do the sine of our 60-degree angle, so we look at our 60-degree angle and we look at the opposite side and compare it to the hypotenuse. Opposite of the 60-degree angle is x times the square root of 3. The hypotenuse is 2x, and that's going to reduce down to be the square root of 3 over 2, just like it did when we did the cosine of the 30-degree angle. They ended up being the same measurement, and we talked about that before. If you look at the cosine of 60 degrees, that's going to be the adjacent side, which is x, divided by the hypotenuse, which is 2x. And that works out to be 1/2. That's the same as the sine of 30 degrees. And then finally, the tangent of a 60-degree angle, that's going to be the opposite side divided by the adjacent side. So the opposite side is x times the square root of 3. The adjacent side is x. Those x's will reduce, and we end up with just the square root of 3 over 1, which if you want, you could just write as the square root of 3. These are things that, as you go through and do trig and do more trig and more trig and more trig in integrated 3, in pre-calculus and calculus, you have to have these memorized. You have to memorize these facts. These are facts just like 5 plus 7 is 12. Fact. Just like memorizing your multiplication tables back in elementary school. 9 times 5 is 45. And you can say, well, Krieger, I never memorized those and I have trouble with those. Well, guess what? In future math classes, you're going to have trouble with trig if you don't memorize these. And a lot of people don't. Trust me. My calculus students struggle with this all the time. It's simply a matter of I'm going to memorize these. Or I'm not going to spend the time and memorize them. And if you choose that path, you're not going to be a successful math student. If you choose I'm going to memorize these, you will be successful in the future. I want to put back up here again the 45, 45, 90 so we can see all of these measurements. So let's get those up here in a snap. All right, and so like magic poof, there is our 45, 45, 90 degree triangle, and there's all the information, the sine, the cosine, and tangent. These, what do we got here? 3, 6, 9 facts you need to have memorized. You're not going to at this point, but it's important in the future that you memorize them, because these are things that are always true, and they're things that we use because we see a lot of 45, 45, 90, and 30, 60, 90 triangles. Let's say that we saw a lot of triangles that were 90 degrees, 20 degrees, and 70 degrees. Then we might take the time to memorize the sine of 20 degrees and the sine of 70 degrees, because it's always going to be the same no matter what. Just like these are always going to be the same no matter what. Every single 30-degree angle, jumping back up here again, every single 30-degree angle has a sine that's equal to 1/2. Every single 60-degree angle has a tangent that's equal to radical 3. Every single 45-degree angle has a cosine that's equal to radical 2 divided by 2. These are all numbers that you can punch on your calculator and make as decimals. We memorize them as fractions. This is true because of these pictures that we learned from other videos. The fact that 30, 60, 90, and 45, 45, 90 always have these ratios. They always have the hypotenuse is set up in a certain way, the adjacent side, the short side, the long side. And so because of that, we have these memorizations that we use. Now, how we use them is going to be in our next example, but we're going to need another slide. So this information is here. I'm going to be bouncing back and forth between this slide and the next slide because we need to have these values as we go about solving triangles. So that's coming in our next slide. And poof, like magic, we're at the next slide. So here we're trying to find the value of x. We can actually do this a lot of different ways. We have a lot of paths that we could take. One path that we could take is to say, well, I know this is a 45, 45, 90 degree triangle, which means it's isosceles, so this side would also have to be 6. And then we could just do the Pythagorean theorem and go 6 squared plus 6 squared equals x squared and solve for x that way. There's nothing wrong with that. Another path that we could take is, let me get rid of that 6. We could go ahead and say, well, I know the facts about 45, 45, 90. In fact, if I jump back to the previous slide, we see that in 45, 45, 90 triangles, this picture, I don't know why I use that marker, let's go with the highlighter, this picture needs to hold true. Which means that the hypotenuse, let me get rid of that, this part right here has to be square root of 2 times one of the legs. So if we go to the example, since one of the legs is 6, then we can easily figure out what the hypotenuse is if we know that setup. That's a second way to do it. I want to show you a third way to do this problem as well. Now, you might look at this third way and go, I would never choose this path. That's okay. Sometimes you're going to be forced to do this path, and that's why we're seeing it here. I just want to stress that in this problem specifically, you could do a lot of different things. What I'm going to do is I'm going to look at one of the 45-degree angles, specifically this bottom 45 degrees. And based on that 45 degrees, I'm going to label up the sides of my triangle. Now, we know one of the sides is never going to change. That's the hypotenuse x. That's guaranteed. The side that I have labeled as 6, based on the angle that I've marked, that is the adjacent side. So then I have to think about, okay, what uses adjacent and what uses hypotenuse? That would be cosine. And so we can set up an equation to do this as well and say we're going to take the cosine of 45 degrees, and the cosine of 45 degrees has got to equal the adjacent side, which is 6, divided by the hypotenuse, which is x. Now, how can I figure out what x is? Well, no problem. I can figure out what x is because I have memorized the cosine of 45 degrees. If we jump back to this other slide, I can clearly see that the cosine of 45 degrees is always radical 2 divided by 2. Okay, so when I come over to this, cosine of 45, I can replace this entire thing, this entire side, with the fraction, the square root of 2 divided by 2. And that's going to equal 6 divided by x. From here, I can solve this. One path that we could take to solve this is to cross multiply. Cross multiplying means I can take radical 2 and multiply it by x to get x radical 2. And that would have to equal this other product of 6 times 2, and 6 times 2 is 12. And then I can easily solve for x by dividing both sides by that radical 2. So dividing here by radical 2 and dividing here by radical 2 will give me that x, do that in black, that x is equal to 12 divided by radical 2. And then we can rationalize that denominator. We don't want to have a square root in the denominator, and so I can multiply by radical 2 over 2, radical 2 over radical 2. We want that fraction to equal 1, and when we do that, we get 12 radical 2 in the numerator, because a radical can't multiply a whole number. In the bottom, we get radical 2 times radical 2, which is the square root of 4, and the square root of 4 is just 2, and then we can reduce that down to be 6 square root of 2. Now, we may have been able to figure that out because it's a 45, 45, 90 triangle, and we know that if, let's do a different color, let's make it yellow, if this side is 6, then this side would have to be 6 times the square root of 2 because I have 45, 45, 90 triangles memorized. Maybe that's the path you take. We could have gone Pythagorean theorem as long as we, like I mentioned earlier, as long as we understand the fact that this has to be an isosceles triangle, so this has to be 6. If we did the Pythagorean theorem just for funsies, we would have 6 squared plus 6 squared equals x squared. And if we do that work, 6 squared is 36 equals x squared. And then if we add those together, we get a 72. And then if we take the square root of that, x would equal the square root of 72. And if we simplify that, the square root of 72 can be written as the square root of 36 times the square root of 2, because that makes 72, and the square root of 36 is 6. See, we get that whether we do it with trig or whether we do it with the Pythagorean theorem. So it's kind of up to you in this problem. On the next video, the next video we're going to look at is just a whole bunch more examples, and on those examples we're going to see that we're going to run into situations where we can't choose a path, that only one path is going to work for us, and it's going to be this trig path. And so that's why this trig path is important. It's important so that way we can do problems when we're stuck with that as our only option. So we got one more video on this, and we're going to get some homework on that video afterwards. So look to that next video to power through the rest of these trig examples, and then we'll get you some homework.